Good morning, friends. In last lecture, we had seen the design of one-way slab. To design means to find the depth required for the slab. Second one, the steel required and the spacing of steel bars required. In that problems of design of one-way slab, we have adopted the design steps. The same design steps are adopted for design of cantilever slab. So today we will start with a problem on cantilever slab. Let us see the first problem. A cantilever slab of effective span 1 meter carries a superimposed load of 1.5 kN per meter square, including floor finish. Calculate the depth and area of reinforcement. Use M20 concrete and mild steel. Take modification factor 1.55. See, in this problem, we have to design a cantilever slab for effective span of 1 meter. See, here we had given directly effective span, that is L effective is directly given. It carries a superimposed load. Superimposed load is nothing but it is the sum of live load and floor finish. We have to consider the dead load. Okay. Then this superimposed load is given as 1.5 kN per meter square, including floor finish. That is just I told you, that is it includes the floor finish. Calculate the depth and area of reinforcement. That is, to design means we have to calculate the depth and area of reinforcement along with their spacing of the bars. So we have to use here M20 concrete and mild steel. Take modification factor as 1.55. See, here we are going to use M20 concrete, that is mixed design is mixed proportion is M20, that is FCK, that is stress in concrete is taken as 20 Newton per mm square, and mild steel we have to use the mild steel bars, that is FE 250 grade steel we have to use. That is for FE 250, that is FY yield stress is taken as 250 Newton per mm square, and modification factor is directly given as 1.55, and it depends on the percentage of steel. So first we will see the cantilever slab diagram. See here, since the total load is acting at the top and it is fixed at one end, this cantilever is fixed at one end and free at other. So if the load is acting at the tip, this cantilever will bend like this in this direction. That is, this cantilever slab will rotate in this direction. The bending will be in this direction, so that the upper layer will get elongated. Where there is a elongation, there is a tension. So for cantilever slab, the main steel is always provided at the top, while distribution steel is provided at the bottom. So here we have provided the main steel at the top and distribution, these round bars are seen, these are placed at the bottom. This is very important. While in one-way slab, the main steel is provided at the top and main steel is provided at the bottom and distribution steel is provided at the top. Vice versa, in cantilever the main steel is provided up and distribution steel is provided below the main steel. That is the main difference. And here the main steel is taken in this direction. See here, this is the direction of main steel and these are the distribution steel provided below the main steel. Now we'll see the assumptions. Here, as per IS code notification for one-way slab, for cantilever slab, we are considering a cover of 15 mm, to raise the bars from the concrete from the bottom. Diameter of main steel we are going to use as 10 mm. Diameter of distribution steel we are going to use as 6 mm since mild steel is given. For cantilever, basic L by D ratio is 7. Then step first, to find the assumed depth or trial depth for cantilever slab. See here, one point is clear that without calculating this trial depth for one way or cantilever or two-way slab, you can assume directly the effective span, and this assumed depth, when you are going to check if it is safe, you can adopt, or if it is wrong, you can change the depth, or you can go through the trial depth for cantilever slab. See, this D is assumed depth. This D is equal to span upon basic L by D ratio, that is 7 into MF. For one way slab it is taken as 20. For cantilever it is taken as 7, that is 7 into MF. MF is given as 1.55. So this D assumed is equal to 92.2 mm, say 100 mm. Then this is the effective depth we have assumed. So to calculate the overall depth, that is from top to bottom of the depth, that is overall depth, that depth D is equal to, capital D is equal to this effective depth plus effective cover. You can add directly the effective cover as 20 mm, or you can consider the diameter of bar by 2 plus this effective cover, that is D is equal to 120 mm. That is, we have assumed this effective depth as 100 mm and overall depth as 120 mm. This is the assumptions only. We are not calculated the required depth. In next step or in coming steps, we are going to check this depth is correct or not. Then next, in given problem, the effective span is directly given as 1 meter. Live load including floor finish is 1.5 kN per meter square. Modification factor is given as 1.55. Material M20 and Fe250, that is mild steel, that is FCK is 20 Newton per mm square, and Fy, that is yield stress in steel, is 250 Newton per mm square. And we have to design a cantilever slab, that is we have to find the depth required for the cantilever slab and steel area. So we'll start with the problems. So in first step we have calculated the assumed depth and overall depth. Then second step is to calculate the effective span. In this problem we have given the directly effective span, that is 1 meter, that is 1000 mm. Then third step, loading for 1 meter wide strip. We are considering while designing any type of slab, that is one way, two way or cantilever slab, we have to consider 1 meter width of the slab. That is, to calculate the self weight or design the slab, we are always considering 1 meter width of the slab. So here self weight of the slab, that is this gamma C, is the weight density of concrete, that is taken as 25 kilonewton per meter cube. Overall depth we have assumed as 120 mm, that is 0.12 meter. Width we have considered 1 meter. This is 0.12 meter. This is 1 meter. Meter into meter, this is meter square. And this unit of this 25 is kilonewton per meter cube. There is this meter cube and this is meter square. Meter square and meter square cancelled. Only remained kilonewton per meter, that is 25 into 0.12 into 1, that is 3 kilonewton per meter. That is the unit weight of self weight. Then live load is given as 1.5 kilonewton per meter square, but we are considering 1 meter wide strip, that is into 1, that is 1.5 kilonewton per meter. So total weight acting on the cantilever slab is 3 plus 1.5, that is 4.5 kilonewton per meter. Therefore factored load acting on the cantilever is 1.5 into 4.5, that is 6.75. That is, here factor of safety we are applying for the load as 1.5, and for steel it is taken as 1.15. So for load, we are considering the factor of safety as 1.5, that is 1.5 into total load 4.5, that is ultimate load or factored load is 6.75 kilonewton per meter is the ultimate load acting on the cantilever slab. So this total ultimate load acting as a UDL for the cantilever slab. So we have to calculate the bending moment acting for the cantilever slab. So in next step, the factored moment MD for cantilever is given by WL square by 2. In one-way slab, when in one-way slab there is a simply supported, that is there are two supports and a live load, that is live load, dead load is acting, total load we have taken, then ultimate load is considered, and that ultimate load is considered as a UDL, and that bending moment is calculated WL square by 8 for one-way slab. But this is a cantilever slab. For cantilever slab, the bending moment is WL square upon 2 because this cantilever is fixed at one end and free at the other end. This bending moment we are learned in mechanics of structure. So this bending moment is WL square 2 for cantilever, that is ultimate load 6.75 into effective span is given as 1 meter, that is 1 square divided by 2. This ultimate bending moment for cantilever slab acting is 3.375 kilonewton meter. See the unit moment or unit of moment is kilonewton meter. If we have to consider this is Newton mm, then kilonewton, to convert it Newton 10 raised to 3 and meter 10 raised to 3, that is 3.375 into 10 raised to 6 Newton mm is the ultimate moment acting on the cantilever slab. Then after calculation of this bending moment for cantilever, we have to calculate, this is the total moment. To resist this moment, the depth which we had assumed in second step, that should be safe. So we have to check the depth which is assumed in last step. So this moment is acting on the slab, this moment must be bared by that depth, so we have to calculate the depth. So next step is calculation of depth, that is determine required depth. See, in last step we have considered the assumed depth, that is 100 mm and overall depth 120 mm. Here we have to calculate the required depth for the given loading, given bending moment. So we have given here Fe 250 mile steel, that is Mu is equal to Mu limiting. We have to equate for calculation of this required depth. This Mu we have calculated as 3.375 into 10 to 6 Newton mm, and for Fe 250 the Mu limiting value is 0.149 FCK BD square. For Fe 415 it is 0.138 FCK BD square. For Fe 500 it is 0.133 FCK BD square. These values must be known to you. So for Fe 250 the Mu limiting value is 0.149 FCK BD square, where FCK is the concrete grade, that is 20. B width we have considered as 1000 mm, that is 1 meter. D square we have to calculate, this D is the required depth for this given bending moment, ultimate moment. So D required is equal to 33.65 mm. After calculation of all these values, we have calculated the D required as 33.65 mm, and we have assumed this effective depth as 100 mm. So as D required, this D required is less than D assumed. This D required is less than D assumed, that is the assumed depth is more than the required, so it can sustain the load. As depth increases, it can bear maximum bending moment. If depth reduces, the bending moment it resists is low. So that we have assumed depth is more than that required for the bending moment. So safe for bending. After calculation of this required depth, we have to calculate the main steel. The main steel is given by the same formula as we have adopted for the one-way slab. That is AST main 0.5 FCK upon Fy into bracket 1 minus under root of 1 minus 4.6 mu FCK BD square bracket complete B into D. See, this minus is at the center. While writing this formula, lot of students are going to write like this: 1 minus 4.6 whole divided by FCBD square. That is wrong. So remember, 1 minus is at the center. 4.6 mu upon FCBD square bracket complete B into D. Put the values of FCK, Fy, all these values B and D, and calculate the main steel area. After calculation of main steel, you have to calculate the distribution steel. So the distribution steel for mild steel for Fe250 is 0.15% of gross area. That is 0.15%, 0.15 to 100 of gross area. That is B into capital D. That is, we have provided 120 mm as the overall depth, 1000 is the width. So AST minimum provided is 180 mm square. Since required area of steel is less than minimum area of steel, provide minimum area of steel as 180 mm square. Then next step, calculation of distribution steel. This distribution steel is calculated as 0.15 gross area, just we had seen. Then next step is spacing of distribution steel of 6 mm. That is S is equal to spacing of distribution steel S equal to 1000 into area of into diameter of bar, diameter of one bar upon total AST. That is, total AST is 180 mm square, and this spacing is 157 mm, say 150 mm. So spacing don't increase. If spacing increases, the concrete will come down. So spacing is always minimized. If it is required spacing is 157 mm, it's okay, provide 157, but don't take it as 160, 165. You do 150 mm, it's okay. Again, its strength increases. So check S is equal to 5D, that is minimum spacing of the bars must be 5D, or S is equal to 450 mm, whichever is less. So we have provided 150 mm, so it's okay. Therefore provide main reinforcement 6 mm diameter at a spacing of 150 mm center to center. Then last step is design summary. Depth of slab 120 mm, cover 15 mm, main steel 8 mm at 275 mm center to center, and distribution steel is equal to 6 mm at 150 mm center to center. This is the design for cantilever slab. Thank you.